what happens is, as you go like to a high number of processes and parallel programs that do solely MPI would introduce, well, more and more partitioning and more and more communication overhead, which means as processor numbers go up, the volume of data that needs to be exchanged, either for neighboring data, for initial data, for broadcast and collective data, goes up and up. And for a while, that's pretty nice, and it's actually pretty efficient, because also MPI processes are good in data locality. Anything a process has inside is within that core, that cache, and has less cache memory. So data transfer goes on the network and doesn't affect the cache so much. Works very nicely. But as communication grows and grows, well, there's more efficient ways sometimes to distribute data between cores that are actually on the same system, either sharing a socket or sharing the same memory. And that then depends on, well, the algorithm that's in it. But if algorithms like here, that's actually the LS-DYNA example, pretty much depends on broadcasting data regularly. The memory copy inside a shared memory node, that can be done like with OpenMP implicitly. Data is just there, it even doesn't need to be copied, so you save a lot of data transfers after a while. That means the OpenMP version can excel much further and surpasses the MPI data locality speed at a certain point. And the penalty of network traffic with MPI becomes so big that it flattens down. At some point, probably the performance of that application even will go down, because there's not enough computation for, well, for getting the computation all done. And at that point, that scales out much further. This is, for instance, used in the car industry to, well, have shapes of what the whole car is, and look at the stress that's put on it when it crashes, when it bumps into something, or so quite a regular thing to do, and people love to have a rather higher performance here. Now, back to the Cluster Studio 2011, have a little update on why Intel MPI is there and why it's particularly fast. There's a number of MPIs out there, OpenMPI, the former HP MPI, which is now Platform MPI. There's still MPI-CH. There's a number of vendors that have their proprietary MPIs. Intel MPI has like three unique points which stuck out and make it particularly nice to use. One of that is it's totally independent of the network architecture, so people can take it and compile a single binary of an. Can I have some water? Sure. Can compile a single binary of an application and move it from a system with just Ethernet to another system with InfiniBand, and not even thinking about the network driver release. Thank you. So that's all taken care of through virtual devices. That meaning the system needs to install like a printer driver, a network driver, and typically with that they come abstract interfaces like OFET, like DUPL, like TMI, like verbs. And Intel MPI just relies on that. Dynamically, typically links at runtime to these. So you can have a single development environment actually on a laptop. Debug, run, compile, release, test, and there you go, and have it released to run on any cluster out there. So it allows ISV vendors to have single releases of something. So that's one unique point. The second is performance. You'll see performance figures in a couple of slides, both in like startup latency, bandwidth on InfiniBand, on Ethernet. There's direct Ethernet support. It's pretty great. But the really unique part is collectives. Collective operations like broadcasts highly depend on the algorithm that's used to transport data through a switch and aggregate it maybe. So instead of having a broadcast that communicates to everybody in a sequential way, you could have a tree where the broadcast master distributes it to a number of nodes or leaves and passes data to all nodes. And for all the collectives, there is a number of differently optimized algorithms available that can be selected either at startup, at configuration time of a cluster, or even at runtime. So that makes it pretty powerful and allows to, well, tweak an actual before unknown cluster configuration optimally to run a certain application even faster. So performance is standing out. The third thing is Intel MPI is very nicely integrated with a couple of tools. It allows for MPI correctness checking by dynamic instrumentation with a single option on the command line, like adding -check. You would be able to completely check boundary conditions and type checking anything that goes through the parameter interface of MPI calls. At the runtime of an MPI application, it would absolutely report anything that violates the MPI standard, any like mismatch of senders, receivers, data types, and thus provide you kind of with an automatic debugging interface. It brings up errors if it sees errors, and anything that it brings up is certainly like something that needs attention, because, well, if it potentially even overwrites data or has a type mismatch, it may work on one machine, it may not work the next run, it may not work on another machine. So checking performance analysis with Intel Trace Analyzer and Connector. It interfaces to debugging, IDV, GDB, total view. It can attach to running MPI jobs. It can be started in interactively with the start of an MPI job.
What are verbs, by the way? What are verbs?
Verbs is an interface that is used for InfiniBand network adapters. Okay. All those network adapters nowadays have processors and memory on it, and actually can offload some of the algorithms, buffering, or protocol that was historically all done by CPU and operating system to the network card. But for that, it needs like a higher level interface that understands how to, well, register buffers, how to register part of the protocol.
That sounds like a mainframe channel, in fact. That sounds like a mainframe channel, running a small computer to actually handle the I/O to the network.
It pretty much goes toward that direction. Yeah. So while DAPL was an abstract interface where one only could make simple assignments or like DMA calls through a call interface, the verbs interface allows for adding attributes, adding buffers, adding parts of the MPI stack, so that there's an offload and a win in latency. It also allows to improve performance in another way. Verbs is the InfiniBand interface that understands that there's multiple ports or multiple cables to a node. And that can be used in a way that's called multi-rail communication. So if there's a single MPI message and there's two cables going out,
send both, the one that arrives first.
It could
wins.
split the message in two halves,
Oh, okay.
and use both cables. Or if there's multiple messages asynchronously, like queued to go out, they would be dispatched to go through that. So that's one of the verbs improvements. Okay, besides like those unique points the Intel MPI library brings with, we have put a lot of work this release into improved startup. So even an MPI program that does not much except like begin end or MPI init and MPI finalize, that needs some time. For a couple of processes, that's neglectable. That's a fraction of a second. If you go to those bigger and bigger machines, it's not so scalable if you think about it very closely. So spawning processes on a node or on a remote node would require you have socket connections, you have file descriptors, and that's all limited resources. You cannot spawn like 1,000 processes without reconfiguring the operating system. So what people have done is have daemons, and MPD was the multi-purpose daemon we have been using for Intel MPI in the past. That was used in a ring fashion, established once and then kick off applications very quickly. Still, I would not call it a problem statement, but if you did run an empty MPI program on 60,000 nodes or so, it's between 30 and 45 minutes, which is not what you want. Hydra replaces that scheme with a tree of daemons. While there is an original daemon that does the MPI startup, it only fans out to like 32 branches, and if there's even more, it goes further down. And it's kind of a replication. Each lower level is a proxy for the upper level and takes information down to start processes, and in an initial phase also takes information back. How many processes are there? What's the identities? What's the mapping? So all that initial information gets communicated very quickly. Turns out, like I've seen a 30,000 core or a process job running in less than a minute a couple of weeks ago on our DuPont system. So there you go. A couple of other replacements or improvements for usability in MPI4 is using SSH as a default, having pinning support with Hydra, having pinning support that nicely works together with the OpenMP runtime that had formerly an own understanding of how affinity and pinning work. So they use now, they're based on the same parameter set and communicate through a joint runtime. There is an API tuner for application tuning that does the following. It would run on a given machine, a benchmark like IMB or like your application with different parameter settings that test broadcast with this algorithm or that algorithm, and then choose a new parameter setting which is running better than before. That way, without changing the application, just by adjusting to how that InfiniBand switch works or how that particular infrastructure is available, chances are applications like ANSYS, LS-DYNA, and all the list you have seen can be improved on a given new system by 10%, 15%, 20%. I think I have a performance slide on ANSYS coming up. Runtime is integrated with CoreArray Fortran, which is like a high-level encapsulation for remote get and remote put.